Near the beginning of this course, we talked about how we build models of mechanical systems from models of mechanical components. The same thing is true of electrical systems. Today we are going to investigate how we model components of an electrical system. You should think of voltage V as being an effort variable, just like force in mechanical systems. The charge Q is like the energy stored in a mechanical spring. Lastly, the current I is the flow of charge from one part of the circuit to another part of the circuit, and is defined to be the time derivative of charge. So I is equal to d dt of Q. Just like we did with mechanical systems, we use what are called constitutive laws to model individual components. These constitutive laws relate variables of interest, like charge Q and current I, to voltage V. For instance, a plot of a constitutive law might look like this one, where the voltage V is on the vertical axis and Q or I is on the horizontal axis. Just like in the mechanical setting, this curve goes through the origin, so if a capacitor has zero charge Q in it, or if a resistor has zero current I running through it, then we measure a voltage between one side of the element and the other that is zero. If, however, the capacitor does have charge, or the resistor does have current running through it, then we expect the measured voltage to be non-zero. The key thing is that these are engineered devices, so the relationship ends up being pretty close to a linear relationship. Electrical diagrams play a critical role in how we set up models of electrical systems, and in this class we are always going to assume that we have four types of components: capacitors, resistors, which you shouldn't confuse these with the springs from mechanical systems, inductors, and batteries. Note that the notation for batteries has some dashes that are larger than others. We will always use these four symbols to represent the four types of idealized components. Moreover, the relationship between voltage and charge of a capacitor is always a line represented by the constitutive law V sub C is equal to 1 over C Q, where the positive number C is called the capacitance. This means that the larger the capacitance, the less voltage V is required to maintain the charge. This is why C is in the denominator. The relationship between voltage and current running through a resistor is also always a line represented by the constitutive law V sub R is equal to Ri, where the positive number R is called the resistance. As a convention, we always indicate the positive end of the battery using large dashes at that end and small dashes at the negative end. We are free to assign current flow conventions any way we like. For instance, let's think about a battery resistor capacitor circuit. So we have a battery, a capacitor, and then a resistor. Now, this diagram represents the elements and the wires that connect them. In this case, there's a battery and a resistor and a capacitor, and here we have a battery and a resistor and a capacitor. We can say that the current runs clockwise in this circuit. Our sign convention for the polarities of the elements that are not batteries will be that the current always runs into the positive terminal of the element. In the case of this capacitor, that means that the positive end is on the right. So we have the current running clockwise, and we end up with a positive sign here because the current is running into the capacitor. We also end up with a positive sign here because the current is running into the resistor, but the battery has the positive sign on this side because that's where the large dash is. Because of the constitutive law, the voltage across a capacitor being positive means that the charge on the capacitor must be positive. So V sub C greater than 0 implies Q greater than 0. The voltage across a resistor being positive means that the current running through the resistor must be positive. So V sub R greater than 0 implies I is greater than 0. Lastly, sometimes our expectations about electrical systems will not always be well aligned with our understanding of the idealized elements. As an example, consider this very simple system. I have a capacitor, I have a battery, and I have a switch. So this switch can be open or closed. When the switch is open, the circuit is not complete and there is no charge in the capacitor. However, the moment that the switch closes, this idealized system predicts that the capacitor will be instantly charged because its voltage Vc will be instantly equal to the battery voltage Vb. That probably seems unintuitive, but that's because real capacitors have what are called parasitic effects that include the non-ideal properties of resistors and inductors. Just like in mechanical systems, keeping in mind the difference between these idealized elements and the real physical elements they represent is a key skill you are developing in this class. So what should you remember from today? Electrical systems also have linear constitutive laws because we engineer them to behave in a linear manner. Remember that we get to choose the current flow convention in the diagram, and that this determines the sign convention we use. Also, keep in mind that just like mechanical systems, idealized electrical elements can have very unintuitive behavior.